Hi everyone, and welcome to Calculating Star Wars Unlimited Perfect Curves. So I've been writing some code the last couple days for performing simulations, and I'm hoping to calculate what is the optimal deck distribution of 2 cost, 3 cost, 4 cost, etc. cards that maximizes the chance of playing something I'm calling a perfect curve. And I'll define that in a second. But anyways, I'm going to talk about all that stuff. What's the perfect curve, the numbers I've crunched. Then I'm going to talk about why these numbers are not useful, but potentially how we could make those numbers useful. So if anyone has any ideas, please let me know. I'm very curious to see if we could actually make this data useful, but right now it's not useful. But like I said, this is just a video blog covering what I've calculated so far, and I've had fun doing it, so figured I'll talk about it. Yeah. So for the next part, I'm going to define what a perfect curve is. I'm going to talk about the results with that definition of a perfect curve. I'm going to talk about why this is not quite useful data yet and what the next steps would be. And lastly, I'll talk about implementation details for people that are interested in the nitty gritty and nerdy stuff. So first, what is a perfect curve? I'm defining a perfect curve when on your 2 resource turn, you get to play a 2 cost. On your 3 resource turn, you play a 3 cost, 4 resource turn, 4, 5, 6, 7. So you are maximally using all of your resources with a single card. And why do you care about this? Well, if you're on your 5 resource turn and you only play a 2 resource card, you left 3 resources on the board that aren't being used, which is, a Knight of Ren. That's a 4/4 that you just left and you didn't play. And if your opponent is able to utilize their resources better, they have a significantly higher chance of winning. And so really, we're trying to maximize our resource utilization. And so by a first degree, I'm just trying to maximize what is the chance of hitting a perfect curve. There are some limitations that I'm sure are popping in people's heads right now, which I'll talk about in a second. But this was a starting definition, and for technical reasons, this is a little bit easier to calculate than some other things that we could have done. Cool. Another minor note is obviously we don't care about the individual cards. So for turn 3, I don't care if it's a Sundari Peacekeeper or Millennium Falcon or something. I'm just saying, what is the chance that I draw a 3 cost and hopefully all of my 3 costs are good. If they're not good, then you should probably take them out and change your deck. But we're just right now hoping that we draw a 3 cost. Cool. Minor note, I'll talk more about this later, but these kind of numbers are probably only useful for sealed and draft constructions. But because again, when you're going against an opponent, there's probably a 3 cost that you care more about, but in sealed and draft, you don't really get to be that choosy. And so you can obviously use this data to just pick what is the optimal curve that you should play with. Anyway, so these are the results. Again, not useful data, but a starting point to think about things. So what these is showing is this is how many 2 cost, 3 cost, 4 cost cards that you should have in your deck. And X means that I only calculated up to a 6 cost. The hit percentage means the percent chance that you are going to actually play a perfect curve. So there's almost a 70% chance with a 30 card deck if you play 8, 6, 6, 5, 5 cards. Cool. So with this perfect curve, this starting distribution, you have a 70% chance to hit the perfect curve. Which is pretty cool. Higher than I would have guessed, but I guess it kind of makes sense. We're only going to 6 resource cost. For 50 card Premier, it's 11, 9, 8, 7, 7, 8. The fact that it goes up is interesting, and I'll talk about in a second. And even if you do everything, only 30% of hands allow you to play perfectly. I'm specifically not doing mulligans. I'll talk about that in the next slide. But this should be higher if you include mulligans, but I haven't quite figured out what an optimal mulligan strategy is. But again, I'll talk about that later. And then I play a lot of data vault, so I was just curious about what this data would look like for data vault. Data vault going up to 7 cost. So like when I play Han with data vault, for example, I want my Keller and Bex, I want my U-Wing reinforcement. So what is the chances I'll do this? Again, we're kind of cheesing because technically with Han 1, you're going to resource cheese and all that stuff, blah, blah, blah. We're ignoring all that stuff. But the optimal distribution would be 14, 11, 9, 8, 8, 10, and that would give you almost a 30% chance to hit the perfect curve. Cool. So one thing that's interesting in this data is you can see there are more 7 cost here than 6 cost, and that is pretty interesting. And I believe that is due to the fact that if, let's say, your initial hand, you drew a 2, 3, 4, 5, 6, 7, unfortunately, you have to resource cards. Even though you have like the perfect hand, you have to resource 2 of them. And so most likely, I mean, there could be some weird cases where you get rid of like a 4 or 5, but for this simulation, we don't know any better. So we're just going to get rid of the 6 and 7. So we had to resource a 6 and a 7. And so because of that, we have to then, within the subsequent rounds, find another 6 or 7. And that can be tricky. But whereas the 2, 3, 4, and 5, we will hold on to those. So anyways, that's why it kind of bumps up at the end. We can see it kind of goes down, and then there's a little tick at the end. What else? I think that's the case anyways. It's possible that there's a simulation error too. All right, going through, what is some more data? So this is the 60 card pass-through rates. So what I'm saying, and this is just kind of just zooming in on one of those rows. So we're saying for 60 cards, round 0, when you play your 2 cost, there are 924 unique states if you play this hand. So this is your 2 cost, 3 cost, 4 cost, 5 cost, blah, blah, blah. So 924 unique states, because there's many ways you could draw like a 2, 3, 4, 5, 6, for example. Like there's many cards that can be swapped in and out, but we don't really, for this simulation, we don't really care what the 2 cost is, so we can collapse all those states. So in total of unique cards from a 50 or 60 card deck, this is the total number of states. There are technically 50 million states, but you can collapse those to just 924. And it's the fact that we can collapse it is what allows us to do this computation. So I say of all the hands, the starting hands, these are the starting hands that have a 2 cost, because that's our only requirement right now is that you have a 2 cost. And you can do the hypergeometric calculators, which we'll talk about later, and show that this data aligns. Then you can do the 3 cost. So we played a 2 cost. Of all the states that successfully played a 2 cost, those get forward to a 3 cost. You're going to draw 2 cards, and then you're going to resource 1. Then there are 5,000 unique states that you could be in after that. And that equivalents to, I don't know, what is that, 562 billion or something like that? Like, it's still within the potential of doing a simulation, but exceedingly on the bounds. It'd be a very long computation to be able to do that. But we can definitely mess with 5,000. Anyways, there's then almost a 70% chance that you'll pass that round. And then just kind of going down, there's a 75% chance, 76% chance, 78% chance, 77% chance, and then a 67% chance. So pretty cool. And to also see, to get to the 8 cost, it is 2.4 times 10 to the 25 states in total. Different ways to get to this, assuming you're starting with a 60 card deck with this distribution. So unfathomably large, but thankfully there are only about half a million unique states, which is totally calculatable. You have to worry a little bit about heap and running out or memory allocations and stuff like that when doing the simulation, but it's not too bad. All right. So I'm going to talk about why this data is currently not too good. First off, is perfect curve really what we want to optimize? I don't think so. So a couple of things. I think probably what you want to maximize is actually resource utilization. For example, maybe it's okay that you play a 4 cost on your 5 cost turn. If overall things just work out a little bit better. That's much harder to calculate because right now, like I said, in the previous rounds, if you didn't have a 2 cost when you're going into the 3 cost, I ignore all those states and I get to do a lot less computation. But I am wondering instead, maybe I should see if I can run the simulation for every single state, which I don't think is possible. But if I could figure out a way to do that and show if you were to play this hand, maybe you used 46 out of the 50 available resources that were played over the first 8 rounds or something like that. I think this is better. Maybe there's a better way to calculate this, or maybe there's like a better metric we should be striving for. But I think what you want is maximum resource utilization. It's not also quite correct because this might also optimize you into using a lot of like 1 and 2 cost cards, which isn't really what you want. You want a lot of big cards because you want to claim initiative. But maybe something in here I feel like is more along what we actually want. I also talk about that later, like the double card play. Like on your 4 resource turn, it's not too bad to play a 2 and a 2. Like maybe it would be better to play a 4 cost because, it keeps more cards in your hand. You have more flexibility. You get to claim initiative. But technically, in terms of value, playing 2 cards on the board actually is a little bit more valuable because cards have innate value. But I don't know. It's hard to balance. If anyone has any good ideas on how to balance that, please let me know because I'm not too sure what exactly we're trying to optimize. And I think maybe that's just what the skill of Star Wars is all about. If a computer could do it, then it makes the game less fun. But it's just it's fun. It's tricky. The other thing I don't take into account is mulligans. Again, kind of tricky. I think I have an idea of what an optimal mulligan strategy should be. But like in the real world, you're going to look for a decent curve in your hand, but you're also looking for cards that are useful for your to go against with your opponent. Like if you're playing against an aggro space deck, you're going to have something that deals with that, space, that deals with space if you think that they're going to win the race. So at first I was doing, do I just have a 2 cost in my hand, if not mulligan? But that's not really an effective mulligan strategy, because if you just drew all 2s, this algorithm would pass it, and that's just a terrible hand. So I think a potential mulligan strategy could be, since I've calculated all this data, I can ask the question, given this hand that I have, if I was to run this hand forward, does it have better odds, given this hand, better odds of me than having a new hand? Kind of like a Bayes' theorem sort of statement to make. Like, given that I know this is my hand, would it be better just to draw a new hand? So I think that would bump up the percentages a little bit. So maybe instead of like a 30% win rate, maybe you'll have like a perfect play rate. Maybe you'll have like a 40% or something like that. I'm just guessing. I think this shouldn't be too hard to calculate, but I haven't tried yet. Cool. This model doesn't take into account multi-cost cards. So pilots are amazing. So like Chewy, for example, can be played as a pilot for 3 cost or on the ground for 5. When you have the cards that allow you to kind of split like that, are just absolutely amazing. But obviously this model does not take into account that some of the cards can do that. And then lastly, again, doesn't match the real world. Like I said, in the real world, leaders have actions that they can do, like Kira, pay 1, do 2 damage, do a shield, but that one, is a great curve filler, like if you need to, or sometimes you're using it, sometimes you're not. Obviously there's leaders. I play a lot of Han 1. You can use for resource cheating, so I might just skip a resource, or maybe I don't draw a 2 and that's fine, and I just resource cheat up to 3. Obviously this doesn't help with that. And obviously, again, like I said, you're going to be looking for cards that work well against your opponent. This is just a baseline. But yeah, like I said, I think really perfect curve is not what we're looking for. I think it's something like maximum resource utilization, but I don't quite know what the metric is. So if anyone has any ideas of what you should be optimizing, please let me know. Cool. So anyways, the future of this model is, I think I'm going to see what the perfect mulligan strategy might look like. If that's actually what we want. I think I need to think more about this, but like I said, now that I know the chance given a hand that it will result in a perfect play, if it is less than 30%, if perfect play percent chance is 30%, and I have this hand, I know it only has a 25% chance of making it to perfect play, then I probably should mulligan. But again, is perfect play really what we want? Maybe I should tackle that first before I start thinking about mulligan strategies. And like I said, is average resource utilization a better metric than chance of perfect curve? Something I need to think more about, or if anyone has any ideas. I think it is. Unfortunately, this is very hard to calculate compared to perfect curve for technical details, which I might cover in a bit. And then lastly, again, should the model allow playing 2 costs on 4? Even if that might skew the model towards choosing more small cards, which I think kind of hurts you long term. Like if you're on your 8 resource turn and you draw a 2 cost, you're not too happy with that. I don't know, tricky, very tricky stuff. Anyways, that's the overview of what I've calculated so far. If you're curious about the calculations, I'm about to cover those. They get a little bit into the nitty gritty, but if not, thank you for watching so far. Hopefully I'll have some more updates in the future. If you have any ideas, please let me know. But anyways, so the nitty gritty of how this works. So what happens is I construct a 50 card deck given some curves. So it has some set of 2 costs, some set of 3 costs, 4 costs, etc. From there, I calculate all of the unique potential steps, the unique states that I could draw. So for example, one unique state I could draw is a 2, 3, 4, 5, 6. I'm kind of combining a couple things in one, but you can imagine I drew 2, 3, 4, 5, 6. That would be a unique state. There are many ways to reach that state. All of these numbers are made up. I'm just using these for example purposes. I'm sure there's probably more than this many ways to get that step, but I'm saying there are 1,927 ways to reach the state 2, 3, 4, 5, 6. Again, I'm kind of skipping forward a little bit. So once I have all of these unique states, for a 50 card deck, there's usually roughly around 700 unique states to start out with. And that equates to about 50 million total states. So again, there's many ways to reach this, but we don't actually care about all the different ways. We just care about like the patterns. Again, we don't care what 2 cost card we draw. We just care that we draw a 2 cost card. So if we had 2, 3, 4, 5, 6, we would resource 2 cards. And so the resource rules over here, first we resource duplicates. So in this hand, I had 2 2s, so I'm going to resource one of the 2s. Then we look for any low cost, so a low cost card that you've already played past the resource turn. So if we're on resource turn 4, we can resource our 2 cost and 3 cost because we don't need them anymore. And then lastly, we resource high cost. It's unfortunate, but we have to resource something. So if in this hand we had 2, 2, 3, 4, 5, 6, we resources the double 2, but we have to resource something else, and all we have left is a 3, 4, 5, 6, so we get rid of the 6. It hurts, and we just have to hope that we get a 6 again in the future. Cool. And so like I said, this is a state. I'm saying that there are 1,927 of these states. There's probably more. I'm just making numbers up. Then this is another unique state. Here we have 2, 2, 6. Now we have a 4, 5, 6. And we just kind of go through, calculate all these unique states. Here's another state, 2, 2, 2, 2, 2, 2. You know, it's going to happen sometimes that you only draw 2 cost. And I'm saying there's 120 of those, blah, blah, blah. So then we have all of these states. We clean them, we prune them, we merge them. Then we go off to a set of 6 rounds or 5 rounds, depending on how far I'm calculating, where you're going to draw 2 more cards, you're going to resource, and you're going to play. So on this state, it looks like we drew a 3 and a 2, or sorry, a 6 and a 3 in this hand. So we went 3, 4, 5, 2, 6, 6, 2, 3. So cool. Again, the details don't matter. We're just saying that we drew 2 more cards, and we resourced one and we played one. And so for it to be a perfect play, we have to play a 3 in this state. We can see down here, I drew a 3, 4, 5, 5, 6. Since I didn't draw a 2, we can't play a 2 cost on our 2 turn. So this state ends and it is no longer a perfect curve play because there's no 2 costs. And so we don't actually calculate any states forward of this. Anyways, so we're just going to keep continuing this. The count gets multiplied. The draw 2 happens with a unique deck associated with each one of these states, so that the deck drawing probabilities still work out. And it'll say like there are this many ways you can draw this combination from this deck, and I do that, and then I multiply the probabilities together, or the total number of states together, and then I merge all those states together at the very end. So for step 2, there are about 5,000 unique states you could be in, with, is that 48, almost 49 trillion total states that you could be in. So quite the reduction, which is very nice. Again, you're going to do that for 5 or 6 more rounds. At the end, for this 6 rounds, this is just a simulation run. There were 650,000 unique states, total states of this many unique states. I think I switched up the terminology, but the 10 to the 25 states was able to collapse into just under 500,000 states. Otherwise, this calculation would not be possible. But yep, you calculate all those. And then what you're going to do is, I'll talk about, actually I'm going to skip forward a little bit. You're going to multiply the dropout rates for each one of those stages. And when you multiply it together, you get the % chance that you hit a perfect curve. Cool. Then as part of that, that is the simulation run for one particular deck distribution. From there, there's probably better ways to do this. I just did a hill climbing algorithm or gradient descent, where I just move a card from one bucket into another bucket. So I move one 2 cost into the 3 cost, for example, and I see if the probability goes up or down. And if it gets a little bit better, then I assume that is a better state, and I just take that and I iterate off of that better state. This assumes there's no local minima. I think that's a fair assumption for this model, but it could be that it's not actually the case, but it should get very close anyways. The only hard, mathy part of this was actually calculating, given a deck that you draw 6 cards, how do you know how do you calculate all the unique states, and how do you calculate the number of states in a unique state? So if you've been playing Star Wars or trading card games for a while, you've probably heard of something called a hypergeometric calculator or hypergeometric coefficients. That is basically what I used. You can use those to calculate the turn 1 probabilities of having a particular card. So this is, if you can go to this website, looks like is that a Star Trek or Stat Trek website? You can say, given a 30 card deck, so we're doing, draft or sealed, I have 5 turn 1 plays. I'm going to draw 6 cards. What is the chance that one of them is a 2 cost? And specifically, we're looking for at least either I have a 2 cost or more than 1 2 cost in my hand, and there's a 70% chance. So that's pretty cool. The probability that I have just a single 2 cost, though, is only 44% chance, but the probability of having at least a 2 or more than 1 2 is 70% chance. So these are hypergeometric calculators. They're very similar to the binomial coefficients. You just kind of multiply some terms together. But anyways, the actual algorithm for calculating this stuff isn't too important. There's plenty of people that have done this stuff before. You can even ask AI to generate it for you. specifically the algorithm, if you want to calculate this up, the keywords that you're going to be Googling are multivariate hypergeometric coefficients. And to calculate the unique states, again, there's algorithms for doing this, but basically it's just an algorithm that splits everything into buckets and then constructs chains based off those buckets, and you do some recursive stuff with backticking to calculate all the unique states. And it's really not too bad. Like I said, AI can do most of the stuff for you. The tricky stuff that made this algorithm possible is because we were able to reduce the state space. And we do that by in two different ways. One is we merge similar states. So after each round, the state space explodes quite a bit, but we can be clever and say that like if two states, it is possible for many states to converge onto the same state. And so we merge those together and we just multiply the count, or add the count in this case, and then continue the simulation. So we don't have to analyze quite as many states. Otherwise that tree just like trickles down really fast. And then also, this particular calculation was possible because we can do dropouts. And so once a curve is no longer a perfect curve, we no longer calculate on it. And so at the end, like I said, we only had about 500,000 states we had to comb through, which is calculatable. If we don't do dropouts, it explodes very fast and it is no longer possible, which is why it is a little bit difficult to calculate average resource utilization, because in that case, you don't care about... in that case, you're continuing all of the states forward, which I think just explodes. Might be possible. I need to do more math. But like I said, you could probably do maybe calculate up to like 1 million or 1 billion states. But beyond that, it's just not calculatable for like doing it on a normal computer. And I'm not going to rent out a data center or something. Cool. So we already covered that. So anyways, if you have any ideas to make this better, or if you have a better metric that would, instead of perfect plays, like average resource utilization or something like that, that'd be much appreciated. If there's a better way to do this math, that'd also be appreciated. I'm pretty sure you have to do these Markov chain simulations. You can't just use a hypergeometric calculator because you have to make a decision each part of the way. Like you can't just do a geometric, like given a 18 card sequence, what is the chance that I have this? Because for example, you might draw a 2, 3, 4, 5, 6, 7 or whatever, and you have to resource the 6, 7. And so it's not, have I seen these cards within an 18 card sequence, assuming you play 6 rounds. It's, that resourcing creates a decision point. And so you have to calculate it each stage of the way, which makes it a little bit harder. I'll put the code on GitHub. I'll just put a link in the description if anyone's there. But yeah, thanks for listening. If you have any ideas, let me know. Otherwise, I'll see you next time. Cheers.